trusted archives of digital public records of computer vision applications, fingerprinting, basically.
Yeah.
Hand over to you.
Okay,
So
yeah, thanks,
Thomas.
Thomas.
You know the score in terms of time.
I'm sure you keep me to it. Okay, great. Well, good morning. I'm excited to share with you this morning a summary of our project Archangel, which is a project that leverages distributed ledger technology to help tamper-proof and assure the integrity of digital archives. And this is a project in collaboration with the National Archives in the UK, the Open Data Institute, which is a not-for-profit organisation based in London, founded by Sir Tim Berners-Lee, looking at open web standards, and the University of Surrey. And it's actually one of several projects that we run in this area of a blockchain for the public good. At the university, we have a testbed Surrey blockchain, and this is one of the projects on it. And I should say that this project is funded by the Digital Economy Programme out of UKRI and the EPSRC. So by way of introduction to this project, I have a short video I'd like to show, and I hope the audio is turned up and will work. So let's try.
Many people consider archives to be about the past. In reality, they're about the future. Archives are lenses through which future generations will see the events of today. Therefore, it's essential that archives are trustworthy. They must be authentic and unchanged accounts, and be able to prove this in a transparent way. As archives become increasingly digital, there are great challenges with keeping records secure for the future. Whilst people often consider digital records safer than hard copies, digital data is much more fragile and at risk, as digital formats constantly change and need updating as technology advances. There's a risk that files may be accidentally corrupted and become unusable. Archangel is a collaboration between the UK's National Archives, Open Data Institute, and the University of Surrey. The project combines two new technologies, blockchain and artificial intelligence, to safeguard archival data in the digital age. Blockchain powers Bitcoin, a digital currency used by millions online. But blockchain has other uses. Archangel proposes blockchain as a way of safeguarding data against tampering and restoring trust in the digital record. In medieval times, pages of court records were stitched together into a patchwork. An obvious hole would be left if anyone removed a page. Today, blockchain uses a similar idea to stitch together blocks of data to detect tampering. Blockchain works as a database that multiple parties maintain. Everyone can check and add to it, but no one can change it. As no data can be modified, the integrity of the historical record remains intact. In a pioneering move, Archangel are combining blockchain technology with neural networks to fingerprint documents. Fingerprints are immutably stored in the blockchain, and when the document is released, the fingerprint can be verified. It will stay the same no matter what format changes occur to the file over time. Blockchain relies on multiple independent organisations to maintain its network. Archangel has been deployed for initial trial across the National Archives of the UK, Australia, Norway and Estonia. Each archive mutually underwrites the archive of the other. Archives across the globe help ensure the integrity of others' archival data without having to share information. Archangel is ensuring an accurate past for a better future through digital archives that are incorruptible. Using this technology, archives around the world will be able to protect each other, checking for accidental and deliberate corruption of data. Archangel will ensure that archives can be trusted forever, not just for study and reference, but for matters as serious as legal cases, official investigations, and for holding organisations and governments accountable.
Okay, thanks for your attention to that video. So, as discussed, the purpose of Archangel is to safeguard the integrity of our National Archives. And if you were to take a stroll through the National Archives, you might see a scene such as this, where we have lots of physical records on shelves. But actually, when we consider the evolution of the National Archives and its digital transformation, it would be better to perhaps consider the archives as looking a little bit like this. We have 5 petabytes of digital video records stored within the archives, including things such as the UK Supreme Court video proceedings which are born digital. They arrive at the archive in a digital form and then are released some years later into the UK's legal precedent. So it's super important that these videos are not tampered with or accidentally corrupted during the tenure of the archive. One of the other interesting use cases around this is the fact that these records are stored for considerable periods of time, and part of the archive's curatorial duty is to format shift the video during its tenure. So if you think about how many video formats you've probably encountered in the last 10 years, you know, these things rapidly become obsolete, and it's part of the archive's duty to transcode the content into playable format using contemporary technology. So with that in mind, I'll just summarise the goals of the project and then particularly drill down into this video use case. I mean, the general goal of Archangel is to ensure long-term sustainability of our digital archives by developing not just new technologies but also new methodologies for curating digital records that leverage this combination of distributed ledger technology and artificial intelligence. And the idea is to explore, or indeed was to explore, the project just finished, 3 different use cases. We started by looking at the use case of research data archives at universities, and then we progressed into the use case of preserving digital images and video within archives, national archives, and we also looked at the use case around delayed disclosure public records and particularly digitised physical documents. So in the video there was, I thought, quite an interesting example of what blockchain is. These rolls here on the shelves are actually medieval court records called the rolls of Chancery, looked after by the master of the rolls, which is the second highest judge in the land. And in these medieval times, the pages of the court records would be stitched together into these large patchworks and rolled up. And the idea was that you couldn't misplace or remove a page of these records because an obvious hole would be left in the roll of Chancery. And really, this idea is kind of quite similar, if you like, to the 21st century idea of a blockchain, where we have effectively a chain of data. Data is committed into the chain in blocks. Each block contains a hash of the previous block, and thereby safeguarding the blocks in the chain. And if you couldn't replace the block with other data without violating that chain of consistency of the hashes. So I guess, you know, I include this slide really probably redundantly to this group of people, but really the points I want to get across here are that whilst blockchain has been popularised through its application to cryptocurrencies, in particular Bitcoin, really, as was introduced by Nigel this morning, it is nothing more than a distributed append-only database. And what we're leveraging here is that data structure to store digital fingerprints of documents in an immutable way. So just as with Bitcoin, we want to store who owns which coins without recourse to a central authority like a bank. In the case of Archangel, what we'd like to do is store the digital fingerprints that we extract from documents without recourse to a single centralized authority like a particular archive. In fact, what we'd like is a chain that is maintained by multiple archives, each mutually underwriting the integrity of the digital record. Okay, so the idea then is that we're taking documents, fingerprinting them somehow, and storing those fingerprints into a blockchain. So how are we doing this? Well, I guess a simplified diagram of the system shown here. We're taking a video. Indeed, we deal with other forms of digital document too, but I'll focus on video in this talk. And then we're fingerprinting that video using a AI technique, if you like, a machine learning technique, using a deep neural network. Why are we doing that? After all, there are many hashing technologies available, cryptographic hashing technologies. Well, it comes from that use case I talked about where we have video that is transcoded over time. If I were to take a video and shift it into another format and then compute some traditional form of hash like SHA-256 or something like that, I'd get a totally different hash. Because if just a single bit of that file changes, or indeed its length changes, then I'm going to come up with a totally different hash. What I want is a hash of that video's content that is invariant to the format in which it's encoded with. And this is what we train our neural network to be able to produce. having obtained that fingerprint, we then store that fingerprint within a blockchain. And as I mentioned, that blockchain is maintained by multiple archives. And indeed, we deployed this technology for trial to 5 different national archives around the world in a 2-month trial. The UK, Australia, Estonia, Norway, and also NARA in the USA, which wasn't mentioned in the video because it was a partner late to join our trial, and the animation company wanted to charge us £200 to add that to the voiceover, which we didn't consider to be a good use of public funding. So there we are. Okay, so well, I won't dwell on this slide, but this is a schematic of the deep neural network that we use to fingerprint the video. The details are unimportant. What I wanted to really describe is that we have this pipeline where we show the original video clip to the network here on the top input. On the middle input, which is called the positive branch of this network, we are showing the network different versions of that video that have been format shifted into lots of different formats at lots of different quality levels. So we're using different video codecs, different audio codecs. And then on the negative branch, which is this third branch, we're artificially tampering with that video by dropping sections of the video out either temporarily, so dropping bits from the start, the middle, or the end of the video out, or possibly obscuring different parts of the video or changing different parts of the video. So we're dealing with spatial and temporal tampering. And the network then learns to tell the difference between changes to the video due to codecs changing, the compression method changing, which are considered benign, and tamperers of the video. And we sample the fingerprint from this later layer in the network. So these fingerprints then that are produced by the network are what we store into the blockchain. But actually, it isn't enough to just store those fingerprints generated by the network, because we need to protect also the network that is generating those fingerprints from attack. Okay? So the way that we do that is by hashing the neural network itself and then storing a hash of that neural network into the chain. So actually, there's 2 hashes being stored in the chain here. The content-aware hash that the network is producing, and also the more classical hash using, in fact, SHA-256 of the neural network itself that produced that hash. And both are being protected then by the immutability of that blockchain. And we could talk more about how we do that later in the Q&A if that's of interest. So the idea then is that at the point of ingestion of a video into, for example, the National Archives, one of these networks is trained alongside the video to protect it. And that network will be of the order of perhaps 100 megabytes or something, so it's quite large, but it's nowhere near as large as the many gigabytes that the video will be. And both the neural network and the video are stored alongside one another off-chain within this large data lake within the National Archives. It's just the hashes of the network and its content-aware hash that are stored into the blockchain. So in fact, the content being stored on-chain is very compact. It needs to be for scalability. And also, we wouldn't want to store the video necessarily on the blockchain, because in many cases, these videos are sort of classified until they're released at a later date. Anyway, having ingested the content in this way, at the point of release from the archive, a member of the public would want to perhaps verify the content that's been released to check it is the same as the content that was placed in the archive in the first place. In order to do that, the user then plays the video through the accompanying neural network to regenerate that content hash, and if it's similar, then they consider that to be a video that has integrity. Okay, so in the Archangel system, just to be clear, what is stored and where? Well, we have this video that is ingested into the archive. We split it up for engineering reasons into clips, and each clip is basically sampled into 30-second intervals, which are then fed through this neural network in order to fingerprint. So we have a sequence of these fingerprints, which is then stored in the chain, and we do that in a compact way by pushing them through an engineering technique we call product quantization, which basically takes these quite long fingerprints and represents them just as just a few tens of bits, actually, that can then be stored into the chain. So within a 32 kilobyte block of data in the Ethereum chain, which is the framework that we use, it's a proof of authority Ethereum chain, we can store enough fingerprints to safeguard about 4 hours of video. And of course, we don't need to necessarily use just one block anyway, so there's no particular limit on that anyway. So how well does our system perform? Well, we evaluated its performance over 3 different data sets. A data set actually from the National Archive of those Supreme Court video proceedings. That's an interesting type of content because it contains very long shots, not a lot of variation in the visual content, but the audio is quite critical. We also compared to footage from the BBC archives, and we had some footage made available to us of various sporting events, including the 2012 Olympics. The performance of the system, I mean, the takeaway message from this slide is that we could detect within a video of approximately 2 hours long tampers of 3 seconds or more. And that's using these compact hashing technologies that we developed during the course of the project. And we noted that there wasn't a particularly significant decay in accuracy correlated with the duration of the video that we were hashing. And I should say that we are hashing both the content and the visual, both the audio content and the visual content within the video. Because we're using a proof of authority chain, not a proof of work, like for example Bitcoin, we don't have this mining overhead and horrific environmental sustainability issue that we would otherwise have. And indeed we get quite a significant throughput on our chain, and these are some of the statistics that we gathered during the 2-month trial of our system with those 5 national archives around the world. We also gathered some user feedback. I mean, the archives were very excited about the use of blockchain for digital preservation in this way. They thought it was quite unique. In some cases, quite surprised by this alternative application to blockchain, which many had considered to be only useful within the domain of cryptocurrencies. We have excerpts of these transcripts on our website, which I'll give you the link to at the end if you're interested in reading more of this. Many archives seeing this as having real potential as something that could scale beyond the length of the project and perhaps be deployed for the long term as a way of safeguarding their digital archives. One thing I'd like to close on is an alternative application we developed for Archangel to a completely different domain, the domain of journalism, towards the end of our project. Obviously, we're all aware of fake news. It's very much in the media, a problem of our time. And an issue that we have, I think, at the moment is that it's very easy to reshare digital content, but not so easy to establish the veracity of that content. And perhaps people share content a little bit too readily online at the moment. And this is a particularly significant problem for digital imagery because an image, carries a degree of evidential quality to it that and this is a problem actually it's not a new problem. People have been creating fake images for some time. So we have developed a technology, again, just leveraging this fact that if we were to take a hash using a traditional technique of an image, then actually it wouldn't be good enough because when you upload images to social media platforms, they tend to format shift them for distribution on their platform. So this traditional hashing technique wouldn't work, but using our AI-based fingerprinting technique, we can reliably match content that has been format shifted as is shared across the internet, as it's distributed across the internet. So if you think about our system for Archangel, substitute the archives for journalistic content providers, like freelance photographers perhaps, the BBC perhaps, although they weren't a partner on this particular project. And then this content fingerprinting technology then allows us to determine the provenance of visual content and check whether it has been tampered in any way. So we built a demonstrator of this, and here's some screenshots of it. It was actually built as a browser plugin, and the idea here is that as you're browsing the internet, any images that are of basically a large area on the screen get fingerprinted and checked against this journalistic blockchain, and then if the image is found in the blockchain, you get a little tick mark, or potentially if it's found in the blockchain and known to be a fake image, you could also flag that up as well as like a known fake. And what you might choose to do is warn the user perhaps if the image wasn't in the blockchain, or perhaps more usefully what you'd like to be able to do is just click on the icon and unpack the provenance information, showing that, for example, the BBC put this image on the blockchain 2 years ago versus perhaps an image that might have been put on the blockchain two days ago that supposedly shows Obama still being president or something like this. So yeah, anyway, this is just a prototype that was built out of one of the mini projects we had exploring different impact areas for Archangel beyond its main domain, and we thought it was a really interesting way to go to tackle this problem of content authenticity. After all, you could tackle content authenticity from the point of view of writing algorithms to detect deepfakes or fake content. People have gone down that route, but ultimately it's an arms race, right? People will always make better deepfake generation algorithms, and then you have to make better deepfake detection algorithms and so on. I mean, we personally think that the better way to approach this problem is looking at content provenance and just allowing people to trace back the provenance of an image to its source, and then actually make their own mind up as to the trustworthiness of that source. So in conclusion then, what I've presented here is our project Archangel, which combined blockchain and AI technologies to protect the archival record for digital preservation. Why did we use blockchain? Because we wanted multiple independent organizations to mutually underwrite the digital record. So we didn't want any centralized point of trust. We wanted to move away from this institutional model of trust, in other words, trust me, I'm the National Archives, to a technological underscoring of trust, which is provided by the decentralization of the blockchain. Why did we use AI? Well, because we wanted to compute a content-aware hash, a hash that was invariant to the format that the video was stored in. And as you saw, we explored this for images and other formats as well. And this particular technology we developed was able to protect videos that were hours in length for tampers of about 3 seconds or more. And we verified the value proposition of this in live trial with 5 different National Archives. In further work, I think there were some really interesting questions that remain around standardization, not just of the fingerprinting technology, but actually the way in which we can store a neural network. And the National Archives separately have stated they're very interested in this. You know, increasingly decisions are made autonomously in our society by AI-enabled algorithms. They're interested actually in archiving those networks that make those decisions, but how can we do that with a system, a technology that's moving so fast? And finally, we've shown that there are applications for this technology beyond digital preservation, for example, for content provenance and deepfakes, and we're actively looking to explore that as well. So I'll end on this slide with a link to our website that contains technical papers that describe our system, as well as various news and presentations we've given on the technology. It's a huge team effort between Surrey, the National Archives, and the ODI, and these are all of our collaborators here. I'm happy to field questions either now or via email, and I can redirect questions as appropriate to the team. Thank you. I have several projects in adversarial machine learning, yeah.
But so why doesn't the fingerprint doesn't get attacked by adversarial learning? Why can't I just learn how to insert the audio sequence in? How do you know that your thing is protected from attack?
Yeah, it's a good question. I mean, we've mitigated against that risk by training a network for each video that we ingest into the system. So what we didn't want to do was produce a single neural network that fingerprinted all videos submitted. I mean, for one, it would be hard to generate such a network that would generalize to all possible content the archive might receive now or indeed in the future, but also specifically because we wanted to mitigate against this risk that someone would then be able to get a hold of that network, which of course they would trivially because it would be public, and then find a way of attacking it. So by, I guess, sort of divide and conquer, by having a network for each video, we mitigate the risk of someone creating an adversarial attack against like all. Yeah. Yeah, sorry. I'm happy to.
Question from the back there, please.
Well, we didn't want a centralized authority for example, a centralized provider of a signature. We wanted a decentralized trust model for this particular application. So in this case, you would require more than 50% of the archives on that chain to collude to sort of to enable history to be rewritten, which we assert wouldn't happen. I guess stranger things have happened in international relations. Yeah. Mm. 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 So yes. So the idea, yes. I mean, it doesn't protect against all attacks. So I mean, certainly you could have a denial of service situation where an entity just basically refused to release the video or deleted the video, and we certainly can't protect against that. To some extent, that authority is still centralized. But in terms of the extraction of the fingerprint and the storage of that fingerprint, that is a decentralized part of the system, right? That is what we're storing on the blockchain. So perhaps there's a misunderstanding there. Yeah. 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 Yeah, that's a great question. Obviously, there is at the moment quite a high computational cost of training a network per video to protect it. But I mean, this is a proof of concept, and we're looking to a future scenario where that cost is significantly reduced. If you think about where we were, about 3 years ago, it would take 3 to 4 weeks to train a network from scratch to recognize ImageNet, which is a standard benchmark data set for object recognition. You can train a network now on commodity GPU in less than a week to do that. So perhaps in a few years' time, we might be talking about considerably less. I mean, this network in itself, it's actually not a classification network, so it doesn't have a softmax layer, it's a triplet network. So actually, this particular kind of network that we've designed here doesn't take quite as long anyway as something like ImageNet to train. And using our system, you could train it in it's about 4 or 5 hours, but that's on a single GPU. I could imagine a scalable cloud solution would do better, and in 5 years, maybe a lot better. So yeah, but it's certainly a valid limitation. Yeah.
That brings this presentation to a close.